Now let's recall what we were discussing in the previous lecture. Well, let's actually give a formal definition of a Taylor series. So, definition. Given a function f of x that is differentiable infinitely many times at 0, the Taylor series for f centered at 0 is given by the sum and from 0 to infinity fn of 0 over n factorial times x to the power n, right? The same formula that we came up with last time. Further, Tn of x, let's call this Tk of x, equal to the sum from 0 to infinity, oops, not from 0 to infinity, it's 0 to k, this is a k partial sum of your Taylor series. And this is going to be the k Taylor polynomial. And Rn of x, or Rk of x, equal to f of x minus Tk of x. This is a kth remainder. And so, if we want to establish whether or not a function is equal to the sum of its Taylor series, then what we would need to demonstrate is that the difference, or the kth remainder, is going to go to 0 as k goes to infinity at a given x, right? Okay, so that's what we need to show. And we have a theorem due to Taylor that states the following. So let the function f be defined on the interval AB, and suppose that n plus first derivative of f exists on AB. Then actually one more thing here which I forgot. Let's suppose one more thing. I'm going to assume that 0 belongs to the interval AB, which means that A is negative and B is positive. Exists on the interval AB, so then for every x in AB, there exists a y in the interval from, I'm going to write from 0 to x, assuming that x is positive, but x can be negative, and it is going to be from x to 0. So y is from in the interval from 0 to x, such that the remainder are n of x is going to be equal to n plus first derivative of f evaluated at y divided by n plus 1 factorial times x to the power n plus 1. All right, so what this theorem allows us to do, it allows us to estimate the remainder in terms of values of partial derivative of the function f. And then if we have information about partial derivatives of f, well, actually, not partial derivatives, n plus first derivative of f, if we have an information about this derivative, then we should be able to estimate the remainder. And if we're planning to show that the remainder is going to 0, then this formula at least gives us some means of computing that. So then again, recall that our principal goal right now is to show that a function f of x is equal to the sum of its Taylor series, right? Like we were discussing before. For the function e to the power x, we figured out that its Taylor series looks like this, but whether or not e to the x is equal to the sum of a Taylor series, we don't know. So that's what we're going to try to establish by using the Taylor theorem. Okay, so to prove this, we're going to use an auxiliary function. So we're going to define capital M to be a unique solution of the following equation. F of x is equal to the sum k from 0 to n, fk of 0 over k factorial times x to the power k plus m times x to the power n plus 1. Yep. Divided by n plus 1 factorial. Okay, let's examine this equation. What we're seeing here is that, once again, we're trying to relate the remainder to, right, our goal is to relate the remainder to the derivatives of our original function. So I'm writing f of x essentially as f of x is equal to the Taylor polynomial, right? And then I have to relate this quantity here to the remainder, right? So this basically is Rn of x. But rather than writing this Rn of x, I'm writing it in a slightly different way. I'm writing this as basically the same term as the term of as a general term of my power series, except that I'm replacing the derivative by this number m, right? Essentially, for the Taylor series, right, I'm going to have a summation from 0 to infinity. I'm replacing that summation by a partial sum from 0 to n, and then I'm trying to write the remainder in the same way as the first term of a series that I'm neglecting, and I'm just writing what would appear to be a partial, would appear to be the n plus first derivative of f. I'm replacing it by m, where m is some number. And then clearly f of x is a number, this is a number, this is a number, so there must be a unique solution to this equation. Okay, so then what we're going to do, so next I'm going to define another function. And I'm going to call this function g of t. And g of t is going to be the sum k from 0 to n fk of 0 over k factorial times t to the k plus m times t to the n plus 1 divided by n plus 1 factorial minus f of t. Okay? So basically what I did, I just took this expression that I have written here. All right, this expression is computed at x, right? And then I'm releasing x, and I'm allowing x to be a variable, right? So then what do I know? I know that if I insert t equal to x here, right, then on the right-hand side, I'm going to get 0, right? Because x satisfies this equation. So then g of x is 0 by star, where star is this guy over here. Again, in my computations that I'm doing here, I'm assuming that x is fixed, right? Because I'm trying to find the expression for the remainder at the point x. All right, so g of x is equal to 0 by star. Also, for the lack of better things to do, let's compute g of 0. What is g of 0? Well, if I'm computing this sum, if I plug in t equal to 0, just like what we're doing during the previous lecture, if I'm looking at a sum where the first k is equal to 0, then for the first element I'm raising t to the power 0, 1. There is no t in this expression. So for sure I have a 0 of derivative of f evaluated at 0 divided by 0 factorial. So that's f of 0. And then if I plug in any 0 into any other term, that term is going to have t to the power some positive number. So if I plug in 0, those guys are going to be 0. So there'll be no contribution from those. Same thing for this term, right? I have t to the n plus 1, so plug in 0. I'm going to get 0, so no contribution from that. And minus f of t, evaluated at t equal to 0, minus f of 0. So this is equal to 0, right? Okay, so we have that. Well, have we seen recently any theorem where we had a function which was equal to 0 at two endpoints of the interval? Yes, we have, right? And that was Rolle's theorem. And Rolle's theorem allowed us to conclude something about the derivative of the function in your interval. So in this case, one more thing before I can apply Rolle's theorem, besides the function having the same two values at different endpoints, let's also notice one more thing. G of t is going to be what? It is certainly a continuous function, right? Because f of t was assumed to be differentiable on the interval from a to b. So f of t should be differentiable, in particular on the interval from 0 to x. And f of t should be differentiable, right? Because it's differentiable n plus 1 times. So it's differentiable once. And everything else here is a polynomial in t, so that is differentiable and continuous. So differentiable as many times as you want also. So g is going to be continuous on the interval from 0 to x and differentiable on 0x. Again, without loss of generality, I'm assuming that x is positive, and if x was negative, I can do the same thing, except the interval will change to x0. Okay, so then by Rolle's theorem, I'm guaranteed that there exists, let's say, x1 that belongs to the interval from 0 to x, such that g prime of x1 is equal to 0. Okay, fine. Now let's compute what g prime of x1 actually is. So here, g prime of t is what? It's a sum. When I take a derivative of the first sum, k will come down. And when k comes down, it will then cancel the first term when k is equal to 0. So I can start from k equal to 1, go to n. Well, am I going to n or am I going to something less than n, right? Because my polynomial here is an nth degree polynomial, so if I take a derivative, right, then it is going to be a polynomial of degree n minus 1. But I'm still going to, up to n here, f k of 0 divided by k factorial, and then k times t to the k minus 1 plus, you take a derivative here as well, so m times n plus 1 t to the power n over n plus 1 factorial minus f prime of t. And so now I can try to simplify this. So k cancels, n plus 1 cancels, and k factorial and n plus 1 factorial become k minus 1 factorial and n factorial respectively, right? So this is in a sum k from 1 to n, f k of 0 divided by k minus 1 factorial t to the k minus 1 plus m t to the n over n factorial minus f prime of t. All right. And actually, let me simplify this a bit further. So this is the same thing as, and let me use a different different index here. So let's say L is going to be equal to k minus 1. Then we have a summation. If k starts from 1, L starts from 0. It goes to the n minus 1. And then we have, so k is going to be equal to L plus 1. So we have f L plus 1 evaluated at 0. Then L factorial. Then t to the L. And then everything else is the same. And then I said that I'm using this index as a, so L is a dummy index, so I can then replace it again by k, and that doesn't change any meaning. So let's now denote L by k, so k from 0 to n minus 1, f k plus 1 of 0 over k factorial times t to the k plus mt to the n factorial minus f prime of t. Okay, so I already know that g prime of x1 is equal to 0. So now I'm going to compute g prime of 0. Okay, what is g prime of 0? Once again, I start with a sum. So every term in this sum is going to be 0 because it has t in it, except for the first one where k is 0. So where k is 0, t to the 0 is 1, 0 factorial is 1. K is 0, so 0 plus 1 is 1. So I have f prime of 0. If I evaluate the second term at 0, that's 0. And the third term at 0 is minus f prime of 0, so g prime of 0 is 0. Now, just like before, the function g prime what do I know about its continuity differentiability? So the interval from 0 to x1, right, is embedded inside the interval from a to b. The function is differentiable n plus 1 times, so that means that the derivative itself, the derivative of f, is also a differentiable function everywhere on the interval from a to b, therefore is differentiable on the interval from 0 to x1. And then the rest, again, are power functions of t, and is a polynomial in t, so it is differentiable as many times as you wish. And so, therefore, from here, we have that g prime is continuous on AB and differentiable on the open AB. And so then we have conditions of the Rolle's theorem satisfied. So then by Rolle's theorem, we have that there exists an x2 that belongs to the interval from 0 to x1, such that g derivative of g prime is equal to 0. Derivative of g prime is g double prime, so g double prime of x2 is 0. All right, so we know that. So now let's go through the same computation as we did over here, but now for g double prime. So who is g double prime? G double prime of t is the derivative of this, right? So derivative you take again, derivative of the polynomial, you will take a derivative term by term. So you have a sum. Once again, the first term will disappear because it's a constant. So sum from k equal to 1 to n minus 1 of f k plus 1 of 0 divided by k factorial times k t to the k minus 1. Then plus mt mn t to the n minus 1 divided by n factorial and minus f double prime of t. And I can do the same sort of manipulations with this as I did with the derivative. So this should be equal to, so first of all, n and k will cancel out. So this would be a sum k from 1 to n minus 1 f k plus 1 of 0 over k minus 1 factorial t to the k minus 1 plus m t to the n minus 1 over n minus 1 factorial, because n will cancel, minus f double prime of t. And I again can change the index, make L equal to k minus 1 so that k is L plus 1. Then my sum is going to be from L equal 0 to L equal to n minus 2, right? Because L is 1 less than k. Then my k plus 1 becomes L plus 1, so derivative is L plus 2 evaluated at 0 over L factorial times t to the L. Rest is unchanged. And then again, I use the fact that L is a dummy index and I replace L by k again. So this is a sum, k from 0 to n minus 2, f k plus 2 of 0 over k factorial t to the k plus the rest. Okay, and we already said that, so already know that g double prime of x2 is 0. And we want to compute g double prime of 0. So what am I getting? I'm getting the same thing as before. When t is equal to 0, only the 0th element survive, and that is f double prime of 0. Nothing will contribute from the m term, and the last term is just minus f double prime of 0. So the whole thing is 0. And just as before, g double prime is continuous on 0 x2, closed, and differentiable on 0 to x2 open. And therefore, by Rolle's theorem, there exists x3 now between 0 and x2, such that derivative of a second derivative, that's a third derivative, g triple prime of x3 is equal 0. All right, so we now established the pattern. So clearly we should be able to continue this process a number of times. What number of times? Until we exhaust everything, all terms in the sum, right? So when are we going to exhaust all terms in the sum? Well, let's see. So when I took one derivative for g prime, I have n minus 1 up here. If I continue like that, so for g double prime, we end at n minus 2. So for g triple prime, we have to end at minus 3. And I keep going. So how many derivatives should I take? before I see a constant. I have to take a derivative n times, because in that case, I'm going to end up with n minus n here. So then I'm taking derivative, I'm taking a sum from 0 to 0, so that means that that sum is only going to have a 0 term. And each time I have taken a derivative, then I have to increment, right, the derivative, the number of derivative by 1. So for first derivative I had k plus 1, for second derivative I have k plus 2. So if I take nth derivative, so gnth, so gnth of t is going to be, so just the term with k equals 0, and it's n plus it's k plus, it's k from 0. Okay, let me just write the sum. It'll be much easier to see that. So it's a sum from 0 to 0, f k plus n of 0 of k factorial, and then t to the k, plus, and by the way, in this term, right, I started from n plus 1, so if I take derivative n times, I'll just have mt left, right, because if I take derivative n times, I'll have n minus n factorial on the bottom, that's 1, and then t to the 1, so and t to the 1 remaining there. So m just plus mt minus f nth of t. And this is nothing but, so when I evaluate this expression at k equal to 0, and that's only k that is allowed here, I'm going to get f nth of 0 plus mt minus f nth of t, right? And I know, because on each step I'm going to apply Rolle's theorem. So after total n steps, and there is an xn that belongs to the interval from 0 to xn minus 1, xn minus 1, and the interval is an interval from 0 to xn minus 2, etc. So all of these actually are between 0 and x, right? Because on each step, a new point belongs to the interval from 0 to the previous point. So that means that xn is still between 0 and x, such that gn of xn is equal 0, right? All right, but also if I compute now gn at 0, right, then it's clear from here that that is f nth of 0 plus plus mt at t equal to 0, that is 0, minus fn at 0, so this is again 0. This function is differentiable, right, because mt is differentiable. Nth derivative of t is differentiable because we assume that f is differentiable n plus 1 times. So once again, this function gn of t satisfies the conditions of Rawls' theorem, and gn satisfies the conditions of Rawls' theorem. On the interval from 0 to x, to xn. And therefore, by Rawls' theorem, there exists y in the interval from 0 to xn, which is again subinterval of the interval from 0 to x, such that subinterval such that gn plus 1 of y is 0. But what is gn plus 1 of y? It's a derivative of this last function that I have written here. So derivative of a constant fn of 0 is 0. Derivative of mt is m minus f n plus 1 evaluated at x at y, and so that's what we got. And so therefore m is equal to f n plus 1 of y for some y between 0 and x. Right, so it's just n applications of, or n plus 1 applications of the Rawls theorem that give us this. But now, what was y? What was m? M was a solution of this equation, right? So then I can just take that equation, copy it, and use the fact that I now know what m is. So therefore, so now what is m? M is nth derivative n plus first derivative of f evaluated at y. Right, and what do I have now? I have now that f of x, let's see, f of x is equal to the Taylor polynomial of the nth degree plus a remainder, right? And so the remainder must be equal to the circle quantity, right? So also f of x is, so this guy is Tn of x, and f of x is Tn of x. Is Tn of x plus Rn of x. And so we conclude that Rn of x, because this guy and that guy are the same, this guy and this guy are the same, so Rn of x must be equal to this expression. So Rn of x is fn plus 1 of y evaluated fn divided by n plus 1 factorial times x to the n plus 1. And that's what we set out to prove. Okay, and so next time we're going to discuss how one can use the Taylor's theorem to actually prove that function is equal to its own Taylor series.